Hello students, welcome to my channel again. I hope that my previous lecture of UV laser you might have attended and you might have enjoyed that lecture. And in today's lecture we will be discussing about the construction theory and working of the helium neon laser. So I have drawn an outlined diagram of the helium neon laser. It actually contains a discharge tube which is filled with two gases. One gas is helium and another gas is neon. The concentration of the helium is 10 times that of neon. The approximate size of this tube, its diameter is of the order of 1 centimeter and length is of the order of 80 centimeter. If you have attended my lecture on the functioning of the electric discharge tube, there I explained you that actually the length of the tube and the concentration of the gas and the potential difference between the electrodes are actually interrelated. So if you change the dimensions of the tube or concentration of the tube, or you want to change the battery EMF, then this concentration may not be the same. So therefore different authors may quote a different value in different books. So I am sticking to this ratio, that is 10:1, which is appropriate for this dimension of the discharge tube. Okay, the discharge tube has I have shown the end faces of the discharge tube be inclined. These are slanted at a specific angle. That angle is called Brewster angle. I will discuss later on about this. And there are two plane mirrors outside the tube. One is the totally reflecting mirror and other is the partially reflecting mirror. We know that there are three components of the laser. One is the pump, second is the active medium, and third is the resonator, optical resonator. Now you can see these two mirrors. So we need to identify active medium, pump, and optical resonator. Because this part of the lecture is related with the construction, so I must tell you something about the construction. You can see these two mirrors, which are plane. Their polished sides are inside and their rough surfaces are outside. And one of the mirror is partially reflecting, this mirror is totally reflecting. So these two mirrors combinedly form the optical resonator. So we have now observed what is optical resonator in this diagram. Next, we need to know what is active medium. Actually, the system of two gases, helium and neon, it constitutes laser medium combinedly. And out of these, only neon gas gives the lasing light. So lasing action is given by neon. This just supports the process. What is the role of helium? I will tell you during the explanation of the working of the laser. So this is just supporting medium. So you can see that neon atoms, or you can also say neon molecules, because both helium and neon are real gases, and these are monoatomic. So if I use the word atom or molecule in this lecture, please do not mind, because both of these will make same sense, because I can say molecule of neon and I can say atom of neon. It will not make any difference for a monoatomic gas. So active medium is neon gas and active centers are neon molecules. Next is pump. Now if I erase this upper space, so let us say one of the electrodes is negatively charged, other is positively charged. So between these two electrodes we will apply a battery. Let me just take negative terminal to the left side. So this is a battery of EMF, appropriate EMF. So these two electrodes along with the resistance and key, they act as the pump. Of course, the glass tube you can include it in the pump part. So this glass tube and this battery, resistance and key and the electrodes, all these combinedly constitute the pump. So in this diagram now we have identified all the three components of the laser, which you should be able to identify, distinguish now. Now, how to explain the working of the laser, I must tell you about the energy level diagram. So the energy level diagram of both the molecules will be shown. So if you have not seen my or attended my lecture on the concept of metastable state and 4-level laser, so I would advise you to kindly attend to that lecture first. There I have told you how metastable states of helium are actually formed. So I will use that concept right now. So this is helium. So I would use, let us say this is the ground level of helium. This is the excited level. This is another excited level of helium. So because of the, let us say, less space available to me, I can erase this portion. Rather, I would like to draw the diagram here. Let us say this level is F1, this level is F2. Approximately its energy is of the order of 19 electron volt, and this is F3. These are the three energy states of helium. Its approximate energy value is 21 electron volt. The actual values you can see from internet or from standard books. Now the energy level diagram, if I draw the energy level diagram of neon, then I will use symbols E for designating the energy levels of neon. So this is E1, this is actually E6, this is actually E4, in between them there is E5, here it is E3, and somewhere here it is E2. So E3 is slightly closer to, E2 is slightly closer to E1. Okay, now this is just a coincidence that the energy difference between E6 and E4, that is E6 minus E4, is approximately equal to the energy difference between F2 and F3. So this these two energy levels are of neon, and F3 minus F2, these energy levels are of helium. So for better understanding, I have shown these at equal energy levels. So kindly remember that energy F2 is not equal to energy E4. Similarly, F3 energy is not equal to energy E6. These energies, this energy and this energy is not equal. Similarly, this energy and this energy is also not equal. Actually, the difference of these two energy levels and the difference in the energy of these two energy levels is equal. So we will be using that concept. So kindly again remember that the energy levels of atoms and molecules are their characteristic properties. So we cannot do anything about them. So it will be unique. You might have studied in your lower classes about the energy level diagram of an isolated hydrogen atom. So the energy of the electron in the E1 is minus 13.6 electron volt. Next is minus 3.4 electron volt. Next is, I think, minus 1.81 electron volt. All these energies are fixed. You cannot have different energies of hydrogen electron in an hydrogen atom for E1, E2, E3 anywhere in the world or in the universe. So if you have the same isotope hydrogen everywhere, so the energy level diagram is therefore characteristic property of an atom or a molecule. So this energy level diagram you have to remember as such, and their values are their distinct properties of these values are distinctive properties of helium, and these are of neon. So this energy and this energy are not equal. Similarly, this energy and this energy are also not equal. However, this energy difference and this energy difference is approximately equal. Therefore, for better understanding, we have shown these to be at equal energy level, so that you can be able to understand the things in a better way. Okay. Now, what is going to happen here? The ratio, you should remember that the gas molecules are neutral. This, if you have attended my previous lecture, this I have already mentioned in my previous lecture related with the working of electric discharge pump. And electrons are charged. So the motion of the electrons that are emitted from cathode, this is ordered, and the motion of the gas molecules is random. If you accept kinetic theory of gases, because both of the gases are ideal, so to large extent it will be obeyed by the both of the gases. Kinetic theory of gases is mostly accepted by the obeyed by the by the ideal gases and noble gases rather. So, and both of these gases are noble gases. So the motion of the helium and neon are this is it is a random motion. So Brownian motion you can use, and motion of the electrons which are emitted from cathode, they will be traveling toward anode under the influence of the potential difference. So therefore their motion will be actually ordered motion. Now we have made the concentration of helium 10 times as compared to the concentration of neon. Now please remember that you can think, in fact in my previous lecture one of the student has actually asked about this, that why certain other processes which according to him he think may be taking place were not discussed. But when actually many other processes are taking place, but we will be discussing only that process which is favorable to us, and all other processes which are not favorable to us, even if these are happening, these are taking place, then these will lead to the wastage of the energy. And at the end result of these non-favorable processes taking place in the laser medium will be that the efficiency of the laser will decrease because of the large number of non-favorable processes happening along with the favorable process. So we will be discussing only about favorable processes. Okay. So what is going to happen if an electron will leave the cathode? It will travel toward anode, and under the influence of potential difference, it will gain kinetic energy. When it will gain sufficient kinetic energy, what is going to happen? Let us say the kinetic energy gained by the electron, if it leaves the cathode with zero velocity and all the velocity that it gains is because of the potential difference, then we can very simply write that kinetic energy is equal to simply charge into potential difference. Kindly remember that potential difference is actually divided across this whole length. If I talk about uniformity, let us say the EMF of this battery is E, then the length is 80 centimeter, then the potential difference across the tube will be equal to E volt per 80 centimeter. That by putting the value of E you can calculate. But please remember, the value of E, the EMF of the battery, must be much greater than this. The highest value is 21 electron volt. If you divide 21 electron volt by E, that will give me excitation potential. So a battery of voltage less than 21 volt will not work here, and we need a battery whose potential difference is whose EMF is much greater than that of a 21 volt. Kindly remember. So as soon as the electron will leave the cathode, it will travel toward anode. It will gain kinetic energy, and when it will gain sufficient kinetic energy, at least more than 19 electron volt we require for first excitation. Let us say it acquires some kinetic energy. Kindly remember that these are electronic energy levels. Let us say that electron acquires a kinetic energy of the order of maybe let us say 19.5 eV. Now what will happen when an electron which has gained kinetic energy of the order of 19.5 eV, it will collide with a gas molecule, because there are two kinds of gases, helium as well as neon. So the electron, because it is a statistical process, our molecules are moving randomly, so electron can collide with any gas molecule. Let us say again, my favorable collision is that the electron must collide with the helium atom. So when it will collide with helium atom, what will happen? The 19 electron volt energy will take the electron of helium atom from F1 to F2, and what is going to happen to the 0.5 eV energy? So that will give kinetic energy to the helium molecule. So the kinetic energy of the helium molecule will increase. It means before collision the electron was moving. Before collision the electron was moving with a speed equal to RMS speed, that you can say 3 kT by m, where m is the mass of the molecule and the V is the temperature. So this is root mean square velocity. So before collision electron was traveling with this speed, and after collision electron will be traveling with a speed which will be higher than this value. You can calculate this value since you know the mass of the molecule and the temperature. K is the Boltzmann constant. So the additional energy will give speed. So kindly remember that three kinds of motion can be given by the molecules. One is called translational motion, other is called rotational, and third one is called vibrational. So you have also studied in your own classes that for a monatomic gas molecule the only 3 degrees of freedom are possible, and all these 3 degrees of freedom are the translational. One is the motion along x-axis, another is the motion along y-axis, and another is the motion of z-axis. So kindly remember, a monatomic gas molecule cannot show rotational or vibrational degrees of freedom. It can only show translational degrees of freedom. So it means whatever additional energy molecule is getting, that it will use only for speeding up. So it cannot rotate by using that additional energy. It cannot vibrate by using that additional energy, because its rotational inertia and vibrational inertia both are zero. I will not go beyond that point. However, its translational motion can be increased by even a quarter of energy is given to the molecule. So it means when the electrons will collide with these gas molecules, two things are going to happen. One, within the gas molecules, the outermost electron will get excited. Secondly, the additional energy if the colliding electron possesses, that it will give to the molecule in increasing its speed. So it means if I want to identify which molecules are in the excited state and which molecules are in the ground state in that tube, I want to observe it. The simple answer can be as good as that the molecules which are traveling with their root mean square velocity, these are in the state F1, and any molecule which is traveling with a speed greater than RMS speed, it is either in F2 or it is in F3. Since the electron can collide with the gas molecule at different distances, so therefore certain electrons when collide with the helium molecule, they will take helium molecule to the state F2, and certain molecules will take helium molecule to the state F3. So therefore this is how we will excite the helium molecules. Now I have told you that it is a random process. My favorable process is that the electron which is emitted from the cathode should strike with helium. Now how I can, since it is a statistical process, how can I fulfill my wish or my desire? The answer to this is that we have made concentration of helium 10 times than the concentration of neon. As a result of this, when the electron is traveling from cathode to anode within this tube, then its chances of colliding with the neon molecules are 1 by 10 and that of helium molecules are 9 by 10. So as a result of this, so statistically we are controlling this phenomena just by increasing, we are making it from unbiased to biased process. By increasing the concentration of helium, we are actually playing a trick so that the most of the electrons will collide with the helium instead of neon. Now a very big question will come here, that why we want that the collision should take place with the helium, not with the neon. So it is due to the fact that, and I have already explained it in my lecture where I told you that helium, the excited states of helium are usually metastable states because of the triplet in nature. So kindly remember, both of these states, F2 and F3, these are metastable states. These are long-lived states. So lifetime of this state and of this state, it is of the order of 10 raised to power minus 3 seconds. So what is the benefit of this? So I will again take, if you have been attending all these lectures in this chapter regularly, I will take again my same old example. Let us say our this pump assembly is capable of exciting only 100 molecules in 10 raised to power minus 8 seconds. Now the laser light is to be given by the neon. If we do not use helium, we simply use neon because neon is going to give the laser action. Then what is going to happen if I will excite 100 molecules in 10 raised to power minus 8 seconds? Then in the next 10 raised to power minus 8 seconds, our pump will excite 100 more molecules of the neon. Then what is going to happen, since already 10 raised to power minus 8 seconds have been elapsed, so the first 100 molecules would have already de-excited. It means that if whatever value of the molecules can be excited by this pump in this time, it will limit the intensity of the output light. Means if I have taken the example that this pump can excite only 100 molecules, and during the excitation one molecule can emit only one photon, therefore the output beam cannot contain more than 100 photons. It can be less than this value, but it cannot be more than 100 photons in a time period of 10 raised to power minus 8 seconds. That will infinitely say that the intensity of the light will be very, very small. On the other hand, if I just use helium, then this helium molecules, these are states are metastable states. So when the electron is traveling from cathode to anode, it will excite one molecule, second molecule, third molecule, and these molecules, whatever the electrons are exciting, these molecules will remain in the excited state for larger time, and they will get more kinetic energy, and they will start traveling with higher velocities and more randomly within the tube. However, their chances of de-excitation as such automatically will be very small. At least for 10 raised to power minus 3 seconds, this process will be put on hold. And if I use the same pump, therefore that same pump is capable of exciting, because if I use this lifetime of the order of 10 raised to power minus 8 seconds, this lifetime 10 raised to power minus 8 seconds, both of these states are normal excited states, and the ratio of both of these is 10 raised to power 5, and therefore in 10 raised to power 5 cycles I will be able to excite 10 raised to power 7 molecules, which is a large number. And just assume that only 100 molecules are de-exciting, giving 100 photons, and 10 raised to power 7 molecules are de-exciting, giving 10 raised to power 7 photons. What will be the amount of intensity that will be increased because of this mechanism? You can just imagine. So the amount of intensity that will increase will be approximately equal to the ratio of the lifetime of these two states. So that I have mentioned many times in my previous lectures also. It is just for the sake of revision that I am using it here. So what will happen? So the gas molecules, helium gas molecules, will be excited, and they will grow in numbers, because these are exciting but not de-exciting, because these states are long-lived, and for de-excitation the electron has to flip its spin going from here to here or here to here. So another different mechanism will then take place. What we have done here, that every neon molecule is now surrounded by 10 helium molecules. So it means, suppose this is one neon molecule and I have 10 neon this is suppose one neon molecule and it is surrounded by 10 helium molecules. All these 10 are, let us say, either in F2 or these are in F3. So they have therefore gained kinetic energy and they are moving randomly. When they are moving randomly, they may move close to our neon, they may move away from neon. Kindly think about all these things, because it is a statistical process. We have no control over it. Everything is going to take place. We will be talking in terms of statistics only, statistical nature of the gas molecules only. So let us say these molecules are, let us say, either converging, but during convergence all these 10 molecules, they miss to collide the helium molecule. Why these are converging or these are diverging? Because of the random nature. So they may converge or diverge. For the better instance, let us say these are converging toward neon, but these miss the neon. So what is going to happen? The first neon will miss. Therefore, the second neon molecule will be now surrounded by 20. Now these 20, let us say, are again converging. If the second also escapes from the collision with the neon, then the third neon molecule will be surrounded by 30 molecules. And now you can see, if one or a few molecules escape the collision with the neon, then the chances of other molecules escaping from the collision are becoming very less. So it means soon a stage will come that all these helium molecules, which are automatically prohibited from de-exciting to the ground level because it requires flipping of the spin. However, when these excited molecules, these collide with the neon, then what is going to happen? These will transfer their energy to neon molecules. As a result, these will be de-excited indirectly. These will be de-excited indirectly. The energy will be transferred from helium to neon. So what is the benefit of this? This transfer of energy, you might have seen it, either you can Google it, or the transfer of energy due to collision between two gas molecules can happen in a time which is less than 10 raised to power minus 8 seconds, or even it can be even less than 10 raised to power minus 10 seconds. You can just see that what is the atomic collision scale, energy transfers in the case of atomic collisions. Just search for it on the Google. You will find this answer. The nuclear collisions can transfer energy in a time as smaller as 10 raised to power minus 20 or 23 seconds. And in case of atomic collisions, the energy can transfer in a time which is as small as this. So what is the benefit of this? When the collision will take place, then almost whole of the neon molecules will get the energy from helium. Almost whole of the neon molecules which are in the discharge tube will get this energy from helium, and that too in a time span lesser than 10 raised to power minus 8 seconds. And that is a big advantage, because if we are not using helium, we are using only neon, then what is going to happen? We are exciting neon, then these are coming down. We are exciting more neons, then the already excited neons will are coming down. As a result, even if the pumping is working continuously, the number of neon molecules are not going up. However, if we use this indirect mechanism, we excite helium first, then they allow their collisions to take place with the neon, and then suddenly, all of a sudden, due to transfer of energy of the collision between helium and neon, all of a sudden, in the whole of the tube, the neon molecules will get in the excited state, and some of these will be in the state E6. The molecules which will be in the state E6 will be those who have collided with helium molecules which are in the state F3. Similarly, the molecules in this tube which are in the state E4 will be those which are excited in the state F2. So when it is going to happen, so therefore what is going to happen? These neon molecules are almost all of a sudden in the excited state, and therefore a population inversion will exist. Now, kindly remember there are certain rules for de-excitation. Certain transitions can take place, certain transitions cannot take place, and you have to remember all this. So when the molecules which are in the state E6, these can de-excite either from E6 to E5 or from E6 to E3. And the molecules which are in the state E4, these can de-excite from E4 to E3. And from here to here, we get a spontaneous emission. And this state is again long-lived. This is something which we have to think about. This is a long-lived state. Now, what is going to happen when this transition will take place? It will emit photons of the order of 3.39 micrometer. This is a longer wavelength, lies in the microwave region, and the transition from this to this will produce photons of the order of having wavelength of the order of 1.15 micrometer, and the transition from this to this state will produce photons of the order of 6328 angstrom. This spontaneous emission will produce photons of the order of 6000 angstrom. Now, what is the working of the optical resonator? So the photons which are emitted due to transition from E6 to E5, these will have a wavelength of the order of 3.39 micrometer. And if you remember the working of optical resonator, if these photons are by chance emitted parallel to the principal axis, then what is going to happen? These may grow up due to oscillation, and these may, you can have output light of this wavelength. Similarly, this may also have the output, this may also have been in the output. However, in the Ruby laser, it was unfortunate that there were two wavelengths and we were not able to eliminate both of these wavelengths, but actually both of these wavelengths are closely spaced, and therefore we just mentioned only the average wavelength, that was 6943 angstrom. Here we are fortunate enough, this wavelength is the smaller, this wavelength is the bigger, and the difference in the wavelengths, these wavelengths, is very large. Now, the optical resonator can be chosen in such a way that you get condition of resonance only for this wavelength, 6328 angstrom. You can adjust the geometry of this optical resonator, the distance between these two resonators, that the condition of resonance is satisfied by this wavelength, not by this wavelength and not by this wavelength. As a result, in the output, you will get light of wavelength 6328 angstrom. And this produces perception of color in the red color region. So you will get the light which is in the red region of the visible spectrum. Now the transition from, so therefore out of these three wavelengths, we will get lasing action only between E6 and E3. We will get a lasing action only between E6 and E3. Now E3 to E1, this is not E1, this is E2. So E3 to E2, spontaneous de-excitation will take place. However, we are unfortunate here that E2 is long-lived. So when as the time will pass, the number of neon molecules in the state E2 will grow up. Because this is long-lived, so neon molecules can manage to stay here for a long time. And if the number of atoms will grow up, we have seen that absorption is directly proportional to number of atoms in the lower state, and emission is directly proportional to number of atoms in the excited state. For that you can refer to my previous lecture in which I have discussed Einstein theory of radiation. So out of these two levels, this one is the lower, this one is the higher. If the concentration of this level is increasing, if the number of molecules in this level are increasing, then what will going to happen? Then the absorption of the light may take place, and as a result an upward process which is unwanted may start from E2 to E3. These spontaneously emitted photons they can be reabsorbed by the neon molecules, and as a result this E3 state will get a back pressure, sort of a back pressure. It is a radiation pressure, remember. As a result, the difference in the energy levels, the difference in the number of molecules in E6 and E3 will decrease, and as a result the strength of population will decrease, and it may quench the laser action for a while. So this is therefore unwanted process. We cannot just bear with this, that this number should grow. So instead of waiting for the time during which the neon molecules will come from E2 to E1 automatically, we have to bring them down from E2 to E1 as soon as possible. Means as soon as a neon molecule is de-excited to state E2, we must artificially bring it back to E1, so that this E2 and E3 both always remain a minimum in number. So what we do for that? Just remember that these all are, because the gases are monoatomic, these all are electronic transitions, electronic levels, and all these molecules can show only translational motion. So what is going to happen if we decrease the diameter of this tube? Then since the gas molecules are in the random motion, so what is a molecule in the state E2 will be traveling with higher speed, and a molecule in the state E1 will be traveling with its RMS speed. So in order to bring it from E2 to E1, we can simply remember we want to decrease the speed, and what we can do it by just decrease the diameter of the tube, and when we will do so, then the gas molecules, since the diameter has been decreased, so gas molecules which are in the random motion, their chances of colliding with the walls of the glass tube will increase, and when it will happen, then these gas molecules, when these will collide with the walls of the container, they will lose their kinetic energy, some extra portion of kinetic energy, and as a result these will come back to the ground level, and when this will come to the ground level, then such molecules will again start moving with the RMS speed, and they will again collide with the helium, and the process will repeat again and again. So this is how this helium neon laser works. Now let us check whether it is a 2-dimensional or 3-dimensional or 4-dimensional laser. We know that in every laser we have 4 distinct levels. One is G level, ground level, other is E level. Actually pump is fixed between these two levels. So pumping mechanism takes the atoms or molecules or ions from G to E. Then another is UL level, it is just below G, and other is LL level, it is just above G. And the laser action takes place between UL and LL. All that you have studied in my previous lecture. Let us now see what are the roles played by various levels. Now please remember this helium molecule is getting the energy from the pump. So this G level is actually, it belongs to helium, and it also belongs to this G level also belongs to this neon. But in real sense, if we talk about real sense, then ideally it belongs to helium, because these energy values are not the same. Now the pumping mechanism is taking helium from G to means F1 to either F2 or F3. So therefore excitation is taking place F2 to F3. So these two levels, they combinedly form to make a single level that would be called E level. E level is that level up to which excitation takes place because of the process of pumping. So F2 and F3 combinedly play the role of E level. So we have distinct G, we have distinct E. Now out of these, please do not count these. If you start counting, then you can say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and you can just by mistake say that it is a 9 level laser, which is not the case. No laser is more than a 4 level laser. So count just the roles that are played by the various lasers. So this is G level, all molecules were here before giving energy. This is E level, all molecules are here after giving energy. After transfer of energy, you are not getting laser action from E6 to E5 because of the selection of, we are not getting standing wave formation for this because we are not allowing the resonance to happen for this wavelength. Similarly, we are not allowing the resonance to happen for this wavelength. We are only allowing the resonance or the standing wave formation to happen between the wavelengths due to transition from E6 to E3, that is 6, 3 to 8 angstrom. It means E6 and E3 are my lasing levels. So E6 is my upper lasing level and E3 is my lower lasing level. So I initially said that G belongs to both of them. After that I corrected my mistake. So kindly remember, principally G belongs to helium, E belongs to helium, and E6 which belongs to neon is UL, and E3 which also belongs to neon, it is LL. And please remember, the D excitation from here to here produces light in the visible region 6328 angstrom, which is in the red region. From here to here you have a spontaneous emission which produces random light or very less intense light here of the order of 6000 angstrom wavelength. From here to here we bring the atoms back to the ground state forcefully and no radiation is emitted. It is a non-radiative transition and it is called induced D excitation. Induced D excitation. Actually we have induced it. It was not taking place automatically. We induced it by just decreasing the diameter of the glass tube. And this is what I wanted to say about this helium neon laser. Okay, one thing was remaining, that I have made these faces actually slanted. You could have made it just like as a discharge tube, round. If you got unpolarized light, then there is no problem. You can make these as round. But if you want polarized light, then you have to cut these faces at slant. And this slant must be cut at a proper angle. If I draw a normal here, let us say this normal is to this mirror. Let us say this normal, it intersects at some point A here, and if I draw a normal on this face at this, so at A point, both of the normals meet. One normal is to the mirror, another normal is to this slanting face of the discharge tube. The angle between these two normals, this is IP. This is called Brewster angle or polarizing angle. So what is the benefit of this? So when the light will come out of this mirror, when the photon waves will come out of this mirror and these will be reflecting, and after reflection these will be entering, then what is going to happen because of the polarization by reflection, the output light can be obtained as polarized. This will of course reduce the intensity to half, because you know whenever unpolarized light is reduced to polarized light, the intensity decreases by 50%. So however the light can be polarized, so it will be therefore giving me polarized light. If more important thing about is that why we do not fix these mirrors inside the tube, why these mirrors are fixed outside the mirrors, because this helium gas which is filled in the tube, it has a tendency over a period of time, it has a tendency to stick with the walls of the mirror. So over a period of time, when we will be using this helium neon laser, the mirror, because this mirror molecules are sticking to its wall, so the transparency of these mirrors will be lost, and as a result it will not start, it will stop functioning properly. So it is always good to have mirrors outside the tube, so that only photons strike the mirror and they go back and forth, and we keep these mirrors outside. And please remember, it is a 4-level laser, so you have distinct G, distinct E, distinct UL, and distinct LL. You get light from it continuously. No flashing of light will be taking place. Why? Because of the fact that the lower this level, we always keep it at 0, because from here to here spontaneous emission is taking place, and from here to here de-excitation is taking place through an artificial mechanism, that is induced de-excitation. So because of both of these processes, the number of molecules in E3 level is kept 0 all the time. So as a result, this process of production of releasing light will never stop. So you are going to get light in a continuous fashion. So helium neon laser will be a continuous wave laser. It will not be a pulsed laser. The pulsed laser was the ruby laser, which I have discussed in my previous lecture. So I will stop here. I hope you would understand the various facts that I have explained in this lecture. So in the next lecture, I will discuss with you CO2 laser, and till then I will stop here. It's goodbye from me. Thank you. Thanks a lot.